Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And with that in mind, this video is going to focus on how we assign oxidation numbers to different elements within a compound and within ions. And then we'll look at how we use oxidation numbers to work out whether oxidation or reduction has taken place. If you found this video helpful, please remember to like it, subscribe to the channel, keep checking back because we're adding more content all the time. Yes, so when we're thinking about oxidation numbers are basically charge. In other words, it's a fancy way of saying charge. So for instance, you would not say 1 plus, that is wrong. Instead, you would say plus 1. So you always put the plus or the minus before the number. And what we'll do now is go through the rules for assigning oxidation numbers and look at some examples. Yeah, so the first rule of assigning oxidation numbers is that the oxidation number of an uncombined element is always 0. So for instance, if you had the element sodium on its own, its oxidation number would be 0. If you had oxygen, O2, a bit more of a tricky one because you might say, well, the oxygen is combined to an oxygen. But what we mean is it's not combined to a different element. So its oxidation number would still be 0. If you have fluorine, the element fluorine, its oxidation number would be 0, even though it exists in pairs. So the oxidation number of an uncombined element is always 0. So our second rule then is that the sum of the oxidation numbers in a neutral compound must equal 0. So for instance, if you have water, now, I don't know if I've got these rules in a very good order here because we need to know some of the other rules to assign the oxidation numbers in water, but I'll just go through it anyway. Hydrogen is plus 1, and there's 2 of them, so it's plus 1, plus 1. And therefore, the oxygen must be minus 2 so that the sum of the oxidation numbers equals 0. So for any neutral compound, it must add up to 0. So if you have, for instance, carbon dioxide, CO2, we've just said that oxygen is minus 2, and there's 2 of them. And therefore, we can apply the principle to work out what carbon must be, and carbon must be plus 4, so that all these oxidation numbers add up to 0. And just one more example. HNO3. The oxygen we've said is minus 2, but there's 3 of them. Be careful here. Don't go down the rabbit hole and say the oxygen is minus 6. It's not. It's minus 2, but there's 3 of them. It's a bit like if you've got 3 2-penny coins, you have 6 pence in total, but each coin is still worth 2 pence. You haven't changed the value of the coin. You've just got 3 of them. Hydrogen we've said is plus 1. The only time hydrogen isn't plus 1 is when it's bonded to a metal, but we'll have a look at that in a separate rule. So therefore the nitrogen must be plus 5. So that the pluses add up to plus 6 and the minuses add up to minus 6, and therefore the compound is neutral. So our next rule, the oxidation numbers of the group 1 metals in a compound must always be plus 1. So if we take something like sodium chloride, NaCl, we're saying that the sodium is plus 1. Because it's a neutral compound overall, the chlorine must be minus 1. If you take something like sodium oxide, Na2O, the sodium is plus 1, but there's 2 of them, and therefore the oxygen must be minus 2. And if you have a bit more of a complicated one, Na2SO4, sodium sulfate, we just start applying our rules gradually. So sodium is plus 1, and there's 2 of them. Sulfur we don't know yet, we're going to have to work it out indirectly. The oxygen we said is minus 2. And now we do a little bit of arithmetic. And if the sodium is +1 and there's 2 of them, +2, these oxygens add up to -8. Therefore, the sulfur must be +6. Okay. So our next rule is that the oxidation number of group 2 elements in a compound must always be +2. So if you had magnesium chloride, MgCl2, the magnesium must be +2 because it's in group 2. And then the chlorine, in total, must be -2 to balance it out. But because there's 2 of them, it must be -1, -1. Or if you had magnesium oxide, the magnesium must be +2 and the oxygen must be -2. Or if you had magnesium carbonate, MgCO3, the magnesium must be +2 because it's in group 2. The oxygen must be -2, and therefore the carbon must be +4, so that we add up to 0 in total. So oxygen's oxidation number is -2 unless it's in a peroxide. Let me just deal with that one first. The best example of a peroxide would be H2O2. Now hydrogen is almost always +1, and there's 2 of them. So +1, +1. Hopefully you can see there that the oxygen can't be -2 because it has to be adding up to 0, and therefore the oxygen in this case is actually -1. But that's the exception rather than the rule, I suppose. So normally you'd have something like, let's say aluminium oxide, which we haven't seen yet, Al2O3, where the oxygen is -2, and there's 3 of them, making -6, and therefore the aluminium must be +3, and there's 2 of them. And that takes in another rule, actually. I won't bother making it into a slide because it's probably not worth it, but aluminium is always +3 when it's in a compound. So you could always say aluminium in a neutral compound has an oxidation number of +3. Okay, and then just one more here. If you had something like sodium oxide, Na2O, we've got 2 rules going on here. Oxygen is -2, and therefore the sodium is +1. Yeah, so the oxidation number of fluorine in a compound is always -1. So for instance, if you had magnesium fluoride, MgF2, the fluorine would be -1, and therefore the magnesium would be +2. Or if you had something like carbon tetrafluoride, CF4, the fluorine would be -1, 4 of them, and therefore the carbon must be +4. When it comes to the halogens as a whole, so group 7, they are normally -1, but there are exceptions to that. There's quite a few different exceptions. So I wouldn't typically apply it as a rule. It's easier to apply one of the other rules and therefore work out what the halogen is last. So the next rule is that the oxidation numbers within a polyatomic ion. Now that's a bit of a mouthful, isn't it? Polyatomic. Polyatomic just means lots of different atoms within an ion. So if you've got an ion which has lots of different atoms in it, all the oxidation numbers must add up to the charge that is on that ion. It's probably easier to see this with examples. If you take the sulfate ion, SO4, 2-, all of these oxidation numbers must add up to -2 because that's the charge on the ion. So if oxygen is -2, and there are 4 of them, That makes -8. And we need to get back to -2, therefore the sulfur must be +6. Let's look at another example. If you have the nitrate ion, NO3-, the oxygen is -2. That makes -6 because there's 3 of them, but you need to get back to -1, so you have to add 5, so the nitrogen must be +5. And just one slightly more challenging one, if you have Cr2O7 2-, that's about as hard as it gets. You've got 7 lots of -2 for the oxygen, which gives -14. And therefore we need to get back to -2, so we have to add 12. But because there's 2 chromiums, we would add 6 from each one. So each chromium is actually +6. So you've got +12 on this side and -14 on this side, giving you the 2- overall. And it's not quite a polyatomic ion, but if you have a monoatomic ion, something like the sodium 1+ ion, then the oxidation number would just be +1. Or if you have the magnesium ion, which is in group 2, Mg2+, then the oxidation number would be +2. Or if you had F-, the oxidation number would be -1, and so on. Okay, so we're going to look at how we can use oxidation numbers to solve problems in redox chemistry. We need to know some definitions. Firstly, oxidation. We need to be able to define oxidation. Now, you could say gain of oxygen. Perfectly correct. Doesn't always apply though. There are sometimes oxidation processes that don't involve the gain of oxygen. You could say it's the loss of electrons. That's a good way of defining it. The one we're going to focus on here though is an increase in oxidation number. So we look at a chemical reaction, we see if the oxidation number has gone up or down, and if it's gone up, then that is oxidation. And we could just take the opposite of these terms for reduction. So reduction would be the loss of oxygen, the gain of electrons, or a decrease in oxidation number. It's just the opposite. So let's look at an example. If you take zinc and you react it with copper 2+ ions, you end up with copper and zinc 2+ ions. And we could add state symbols here. Zinc is a solid, copper 2+ would be aqueous, copper would be a solid, and zinc 2+ would be aqueous. The first thing to do would be to go through and assign oxidation numbers. So zinc is an uncombined element, so its oxidation number would be 0. Copper 2+ would be +2. Copper would be 0. And zinc 2+ would be +2. So in terms of working out what's being oxidized and what's being reduced, let's firstly focus on the zinc. The zinc is going from 0 to +2. So the zinc has an increase in oxidation number. So that's oxidation, because it's gone from 0 to +2. Yeah. Whereas the copper 2+ has gone from +2 to 0. That's a decrease. So that's reduction. This is just the ionic equation, by the way. I've omitted lots of the other stuff just to focus on the key things, the important ions. We call that an ionic equation. You normally omit the spectator ions, they're called, the things that don't change in terms of their charge. If you take the blast furnace for making steel, In the blast furnace, you start off with iron oxide, which is your main raw material. You react it with carbon monoxide gas, and what happens is the carbon monoxide is able to convert the iron oxide into iron, and you get carbon dioxide produced. And we need to be able to explain why this is a redox process. Firstly, balance the equation. You'd need 3 lots of CO and 3 lots of CO2 and 2 lots of iron. But that doesn't really matter in terms of the oxidation numbers. But we need to be able to prove, and a typical exam question might be, prove that this is a redox reaction with reference to oxidation numbers. So iron oxide, we don't know what the iron is, but we know what oxygen is. Oxygen is -2, and there's 3 of them, and therefore the iron must be +6, but split 2 ways means it must be +3. And I would rather write it out this way, +3, than writing +6, because +6 is technically wrong. +6 is the sum of both of them. And then we go to the carbon monoxide. We don't know carbon, but we know oxygen. Oxygen is -2, and therefore the carbon must be +2. The iron is an uncombined element, so its oxidation number must be 0. And carbon dioxide, well, oxygen is -2, and the carbon must be +4. So now it's worth sort of going through and working out what's changing. So let's do each element one at a time. The oxygen is constantly staying at -2. So that's not being oxidized or reduced. The iron is going from +3 in the iron oxide to 0. So that's a decrease in oxidation number, so that is reduction. And then the only other thing that's in our equation is the carbon. And the carbon is going from +2 to +4. So that is oxidation. Okay, so we can say that this is a redox reaction because the iron is being reduced from +3 to 0, and the carbon is being oxidized from +2 to +4. A couple of other terms we need to know and be able to define when it comes to this that come up a bit. First one is an oxidizing agent. Now the job of an oxidizing agent is to go out and oxidize something else. That's what its purpose is. Now if it oxidizes something else, it must get reduced itself in the process. So an oxidizing agent oxidizes something else, and gets reduced. So gains electrons. And I could write out the same definition for a reducing agent, but it's going to be exactly the opposite. So a reducing agent goes out with the purpose of reducing something else. It gets oxidized in the process, and therefore it loses electrons. Do you remember the term oil rig for working out whether something is getting oxidized or reduced? Oxidation is loss of electrons, and reduction is the gain of electrons. So if you're ever struggling to remember which way round it is, think of oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Okay, lastly in this video then, I need to just go through a term called disproportionation. It's a bit of a fancy word, it's a bit of a spelling test on this one at the end, if you can spell that one without your notes. But it's basically when an element is both oxidized and reduced in the same reaction. So let's go through an example and I'll show you here. Here you've got hydrogen peroxide, which is one of the weird ones where oxygen is actually -1 and the hydrogen is +1. And then it goes to water where the hydrogen is still +1 but the oxygen is -2. But then it also produces oxygen where the oxygen is 0. So the hydrogen is remaining constantly at +1, but the oxygen is going from -1 to -2. That is reduction because it's going down. But also it's going from -1 to 0, which is oxidation. So this is why this is disproportionation, because the oxygen is both being reduced and oxidized in the same reaction. So here you've got another chemical reaction that is an example of a disproportionation reaction. We need to prove it with reference to oxidation numbers. So chlorine, the uncombined element, is 0. Let's just focus on chlorine for now, actually. Chlorine here is 0. In sodium chloride, it's -1. And in NaClO, well, we're going to have to work it out, actually, because oxygen is -2, sodium is +1, and therefore the chlorine, by definition, actually has to be +1. Do you remember I said that the halogens are not always -1? Well, this is proving its case here. So the chlorine is going from 0 to -1, that is reduction, because it's going down. And it's going from 0 to +1, which is oxidation. And we don't need to really look at any of the other elements because they're all staying the same. Sodium is staying as +1, oxygen is staying as -2 throughout, hydrogen is staying as +1. So it's only the chlorine that's actually changing in this. Talking of hydrogen though, I think there's one other very quick thing I should cover on this. So yeah, the oxidation number of hydrogen is normally +1. So for instance, let's just take water as our example. The hydrogen is not bonded to a metal, so the hydrogen is +1, 2 of them, and the oxygen is -2. However, if you take something like magnesium hydride, MgH2, actually what happens is the magnesium is more electropositive than the hydrogen, so we assign the positive to the magnesium, so it's +2, and therefore the hydrogen has to be -1. So whenever hydrogen is bonded to a metal, its oxidation number changes to become -1. But other than that, it's always +1 when it's in a compound. All right.